All right, welcome to this explainer. Today, we're diving right into a cosmic detective story that has honestly baffled astronomers for decades: the missing heart of the Cygnus loop. You see, for nearly 30 years, scientists have been hunting for a ghost. The Cygnus loop is this massive, beautiful shell of hot gas expanding through space. It's kind of your textbook middle-aged supernova remnant. About 10,000 years ago, a massive star, we're talking maybe 12 to 15 times the mass of our own sun, ran out of fuel and exploded. And when a star that big goes supernova, its core collapses inward, leaving behind this incredibly dense, super fast spinning neutron star. It should be right there in the middle, but nothing. Observation after observation, the center of the loop has turned up completely empty. So, where is the missing heart of the Cygnus loop? Well, take a look at the tiny yellow box right down at the bottom of this X-ray map. You can clearly see the nearly perfect circular shell of the blast wave, right? Except for that weird, bulging region down at the bottom. Astronomers actually call this the southern blowout. For the longest time, researchers were entirely focused on the geometric center of the explosion. But as you can see, that yellow search grid is way, way off to the edge. And it turns out, this southern blowout region is exactly where our prime suspect has finally been spotted, basically hiding in plain sight. So, let's move into our first section: unlocking the X-ray clues. How did we actually spot this thing? Finding a tiny, dark, stellar corpse thousands of light years away means you can't just rely on visible light. You need high-energy X-rays. By zooming in on that southern blowout using incredibly sensitive X-ray instruments from the Suzuki and XMM Newton observatories, researchers found something, well, totally unexpected. The hard X-ray scans revealed a highly distinct, hard X-ray emitting diffuse nebula. And right next to it, a tiny, sharply defined point-like source. This isn't just random background static. This is a highly structured, energetic system. But what exactly is it? Is it actually our missing neutron star? To figure that out, astronomers had to look closely at these specific energy signatures. When they analyze the X-ray spectrum, astronomers measure something called the photon index. Basically, this just tells us how the X-ray energy is distributed. The point-like source here has a harder photon index of 1.6, while the surrounding diffuse nebula is softer, coming in at 2.2. And guys, this is a massive clue. Why? Because this specific energy drop-off is literally the classic fingerprint of a pulsar wind nebula. If that little point-like source is a rapidly spinning neutron star, a pulsar, it's blasting out a blistering wind of high-energy particles. Those particles emit very hard X-rays right at the source, but as they blast outward and create the nebula, they lose energy, giving us those softer X-rays further out. The physics align perfectly. And it gets better. The really crucial point here is this 4-to-1 flux ratio between the nebula and the point source. When researchers calculated the X-ray luminosity of the diffuse nebula and compared it to that tiny point-like source, the nebula was about 4 times brighter. Now, in astrophysics, this isn't just some random fraction. Widespread studies of other known pulsar wind nebula show this remarkably consistent rule. The ratio of the nebula's luminosity to the pulsars is almost always right around 4. The math here is hitting the nail on the head. It heavily, heavily supports the theory that we're looking at the missing heart of the Cygnus loop. But, like any good investigation, we have to look at the other side of the coin. Section 2, Nebula or Galaxy Cluster. Science is all about rigorously testing your assumptions, right? And as it turns out, the cosmos is entirely capable of throwing us the ultimate red herring. Take a look at this comparison because it's pretty wild. The exact same X-ray luminosity, the same temperature profile, and the same apparent visual size on our telescopes could perfectly support 2 wildly different realities. On one hand, it could be our tiny pulsar wind nebula, roughly half a parsec wide, sitting right in our cosmic backyard 540 parsecs away. On the other hand, this exact same data perfectly fits the profile of an unimaginably massive galaxy cluster. We're talking 2 million parsecs across, located 2.5 billion parsecs away. Because of how X-ray brightness and temperature scale over these immense cosmic distances, a distant cluster of entire galaxies looks functionally identical to a tiny stellar remnant right up close. Now, you might be wondering, okay, but what are the odds of a massive galaxy cluster lining up perfectly right behind the exact supernova remnant we're looking at? Well, because the Cygnus loop is so close to Earth, it takes up a massive chunk of our night sky. It has a visual footprint of about 10 square degrees. When you look at deep space surveys, the background of the universe is just peppered with distant galaxy clusters. Statistically speaking, there should actually be about 3 distant galaxy clusters hiding somewhere behind the Cygnus loop's footprint. So there is a very real, fairly large chance that a distant galaxy cluster is simply photobombing our observation.
So which is it? Let's explore Section 3, the high-speed implications, and see what happens if this really is our missing star. The overall properties and the fact that we don't see any visible optical galaxies in that exact spot actually heavily lean toward the pulsar wind nebula theory. And if this truly is our missing neutron star, we have to talk about its incredible escape sequence. Notice the cross marking the geometric center of the explosion. Normally, if a star explodes evenly, the leftover core should just sit right there in the middle. But our suspect is located way down in the southern blowout, a massive 2 degrees away from where it should have started 10,000 years ago. Sometimes supernova explosions are asymmetrical. Basically, one side blows out a little harder than the other, and it kicks the neutron star in the opposite direction like a massive cosmic rocket engine. But to cover that immense distance from the center across all the way down to the southern blowout, in a time frame of just 10,000 years, this neutron star would need a staggering transverse velocity of 1,850 kilometers per second. Let that sink in for a second. That is over 4 million miles per hour. If confirmed, this immense speed would literally make it one of the absolute fastest runaway stars ever recorded in the history of astronomy. Let's see how this builds into an observable phenomenon, something astronomers can actually look for next. You see, a neutron star traveling at this blistering pace doesn't just float peacefully through space. As it moves outward, away from the superheated plasma of the supernova's interior, the star eventually plunges into the much colder, denser interstellar medium outside the remnant. And this collision? It triggers a massive physical chain reaction. Smashing into that colder plasma at such an extreme velocity means the neutron star would be moving at roughly Mach 6, 6 times the speed of sound in that specific medium. It would act like a gigantic cosmic snowplow. This extreme supersonic movement piles up the material in front of it, creating a violent cometary bow shock. Think of the wake left behind a fast-moving boat on a lake, but made entirely of superheated glowing gas. Astronomers know that if they can take higher resolution images in the future and actually detect this bow shock pointed away from the geometric center of the loop, well, that would be the absolute smoking gun, proving this is indeed our runaway star. Which leaves us with this final, fascinating thought for today's explainer. We have compelling X-ray spectra, we've got perfect flux ratios, and we have a missing star that desperately needs finding. But we also have the mathematical reality of cosmic photobombing. So what do you think? Are we witnessing the smoking gun of one of the fastest, most extreme runaway neutron stars ever discovered in our galaxy? Or is the universe just playing a spectacular 2.5 billion light-year optical illusion on us? Future high-resolution observations will eventually give us the definitive answer. But until then, the missing heart of the Cygnus loop remains one of the most captivating mysteries in the night sky. Keep looking up, keep asking questions, and we'll catch you in the next explainer.